An air capacitor with a metal slab. An air capacitor is made by using two flat plates, each with area capital A, separated by a distance d. Then a metal slab having thickness A less than d and the same shape and size as the plates is inserted between them, parallel to the plates and not touching either plate. Part A, what is the capacitance of this arrangement? Part B, express the capacitance as a multiple of the capacitance C0 when the metal slab is not present. And Part C, discuss what happens to the capacitance in the limits A goes to 0 and A goes to D. So looking at this very carefully, I have a positively charged top plate which is going to see negative charges on the metal slab at a distance d minus a over 2. And then there will be positive charges on the other side of the metal slab facing the negatively charged plate at a distance d minus a over 2. So you can see that here I have a capacitance and here I have another capacitance, and the charge that builds up on these two capacitors will be the same because it's the electrons leaving here uh, moving to the top surface will leave behind uncompensated ions of the same charge magnitude but opposite sign, obviously. So the capacitance of this configuration is basically the parallel plate capacitance, but with the distance between the plates being d minus a over 2. So the capacitance C is epsilon 0 because we have air between the metal plate and the top plate. D minus a divided by 2 in the denominator, which gives us a capacitance of 2 epsilon 0a divided by d minus a. And these two capacitors have the same capacitance and they have the same charge, therefore they are connected in series. So two capacitors in series connection is what we have here. So we know that for the two capacitors connected in series, the equivalent capacitance is the product of the capacitances, C squared, divided by the sum of the capacitances, 2C, or 1 over C equivalent is 1 over C plus 1 over C. That's what gives us this end result, which is telling us that the equivalent capacitance is C divided by 2. So we find that the equivalent capacitance of this configuration is, because C was 2 epsilon 0a, this is epsilon 0a divided by d minus a. That's the equivalent capacitance. Now, what is the capacitance of the parallel plate capacitor with air in between the two plates? That's what we call C0. It is epsilon 0, the area of the plates A divided by D. So that's for the scenario when I have no metal in between. So this tells me that epsilon 0A is equal to C0 times D. So for the equivalent capacitance here, I can substitute for epsilon 0A C0 times D. So C equivalent is C0 times D divided by D minus A. So it can be written in terms of C0. What happens to the capacitance in the limit A goes to 0? In the limit A goes to 0, C0 multiplied by D divided by D minus A. Now A goes to 0. A goes to 0. So it's going to be C0 multiplied by D over D, which is C0. So we recover the case with no metal slab. If we have A goes to D, then we will have C0 times d over d minus a. And if a goes to d, that will be d divided by 0. So this will be infinite. So the capacitance will be infinite. That will correspond to a fully metal connection. So what we find is that a very thin metal has no effect on the capacitance. So if you put a very thin metal, it's going to have, with A equals to 0, it's going to have the same capacitance C0. So when A is equal to 0, the thickness of the metal slab is going to 0. That means you have an ultra thin metal sheet here. It will have no effect on the capacitance. As A goes to D, on the other hand, C becomes infinite, and the charge Q is equal to Vc under constant potential will be blowing up as well. So you will have all the charges being collected here. That's because you have an infinite sea of charge, or you can say that we have just the metal connection here. So if you make A is equal to D, then these two plates are connected, then this whole thing turns into a single plate. And the single plate has infinite capacitance. So that's basically not a capacitor anymore. So in this example, we have a parallel plate capacitor with a metal slab exerted in between them. For the capacitance of this arrangement, we note that we have two capacitors connected in series, as you can see here, but the two parallel plate capacitors that we observe are separated by d minus a over 2. So the capacitance is 2 epsilon 0 a over d minus a, and they are connected in series. So the equivalent capacitance is c squared over 2c, product of the capacitances divided by the sum. So the equivalent capacitance is epsilon 0 a over d minus a. And if I have no metal plate, if a is equal to 0, this is going to become epsilon 0 a over d, and epsilon 0 a is c0 times d, so we find that equivalent capacitance is c0 times d over d minus a. For epsilon 0 a here, I substitute c0d. So in the limit a goes to 0, I recover c0. In the limit a goes to d, the capacitance blows up, indicating that you have a metal connection. The charge Q is equal to Vc under constant potential will go to infinity. Why does that happen? This is of course unrealistic, because a metal is an equipotential surface. So you cannot build a potential difference between the two sides of the metal at equilibrium.